have a fairly short presentation today. I want to show you this linear equation has no integer solutions. In other words, there's no place on this line that has integer coordinates, meaning like 3, 4, minus 5, 6, that type of thing. Now, this is fairly straightforward to show. If there was a solution, that's what this says right here. If AB is a member of all the ordered pairs, y'all, and Z cross Z is sometimes called the Cartesian product, but and it's just a set of all possible ordered pairs comprised of integers. Okay, now, so if you take a look at this statement right here, if this were true, we certainly notice that 3 is common to both of these terms, and so we could write down 3 times 5a plus what do we got there? 2b plus 2b equals 14. But notice that 14 has a prime factorization of just 2 times 7. So 14 is equal to 2 times 7. So manifestly, it's not a multiple of 3. It can't be a multiple of 3. So this is equal to 2 times 7. But that means that 14 is never, and we'll just put does not equal 3m. Okay, where m is just some other integer. And let me put the negate through this equal sign. 14 is never a multiple of 3, but the left-hand side is a multiple of 3. So it's clear that there's no solution to this. All right, it's clear that there's no integer solution, but we do know that it's a line. Now, y'all, another way to write this is that the GCD, and this is kind of a general test right here to see if the linear equation has general or has integer solutions. So y'all, this stands for greatest common divisor. The greatest common divisor of 15 and 6 is certainly 3. Okay, the GCD of 15 and 6 is certainly 3, the same 3 that you saw right here. Okay, but we can also use this vertical that does not divide is what I'm trying to say here, folks. Let me erase that. That's not any good. What I'm trying to say is it does not divide. So let's put a vertical line. That's the divide operator, folks. But if you put a slash through it like this, it does not divide 14. And that's just a general test for any type of linear equation. Okay. Again, this GCD is 3. This object right here is equal to 3. Now let's go ahead and move on down and take a look at the line here to make it slightly more convincing, even though that's a fairly straightforward proof. So here's the graph, and I had some computer software to do this, but that's the graph of the equation we just looked at. Now, you'll notice right here that if you take x equal to 0, if x is equal to 0, that gives you the y-intercept, right? So x equals 0, that implies that y is equal to 14 over 6. And that's certainly equal to, what, 7 over 3? So, y'all, 7 over 3 is 2 1/3, right? I'm just trying to convince you this is the line. I could put anything up here, right? But that point right there would correspond to 0 7/3. Okay. Now, so we just said that this doesn't have any integer solutions, but if you take a look right here, this point here looks like it might be equal to minus 3, 10, right? So that point, you might think it's minus 3, 10, right? I mean, it looks pretty close, right? The line. Now, if we go up here, though, and we plug minus 3 in right here, that's 15 times negative 3 is negative 45. And then 6 times 10 is 60. Notice that's equal to 15. Okay, that's equal to 15, which certainly does not equal to 14. I know I'm sticking my neck out to tell you that 15 does not equal to 14. But it was kind of close, right? And so there's some other close ones, like down here, 1, 1 looks like it might be close, but you can substitute in and see it's pretty far off, actually. If you put a 1 here and a 1 here, you actually get 21, right? So that's even further away than it looks. And also up here, you might want to check minus 5 and 15. But they all just miss. So there are no integer solutions. I hope you guys enjoy.